Welcome back. We're just going to take our couple of seconds, ease back into physiology for the day. Okay, welcome. Today we're going to talk about the immune system. Normally we talk about the immune system kind of towards the end of the semester, and at that point in the semester we are going to take a whole week and we're going to talk about the details of the immune system. We're going to explore what physiologically is actually happening when your body encounters a pathogen. But in the current climate, we're in the middle of a pandemic. There's so much misinformation, so much confusion. I think even people who really, really want to be well informed are overwhelmed and exhausted and uncertain. So this is a physiology course, and immunology is part of physiology. So we're going to take this time and just very, very briefly talk about what's happening in your body when you get exposed to a pathogen, and some important points that are relevant to what's happening right now. Okie dokie. All right, so our immunology preview. I really liked this title of this paper. It's really, really appropriate, I think, and accurate. So the immune system complexity exemplified. The immune system is absolutely, wildly, unbelievably complex. A riddle wrapped in a mystery inside an enigma. And then these are little screenshots that I took from this paper. And then in the first paragraph of this paper that's about the immune system, it says, with the exception of the nervous system, the immune system represents the most daunting example of complexity in biology. Indeed, it's a virtual poster child for complexity. And then after that, I evidently cut it off. Okay, so why am I telling you this? I'm telling you this because I want you to know that it's really okay to not understand every detail. It's okay to not understand all the infinite complexity of the immune system. There are people who spend their entire lives studying just one part of the immune system and become experts on that part. So I'm going to talk a little bit about the immune system and give you kind of some handholds. But as we're trying to navigate everything, and as we're trying to navigate understanding and making decisions, remember that it's the process of science that we understand as science students and as scientists, and that we trust. So I also, when I was preparing for this lecture, felt extremely overwhelmed. And I reached out to someone that I know who is an immunologist. And Dr. Samantha Le Sommer, I believe is how it's pronounced. I reached out to her. She's an immunologist. She has a PhD. She's completed 2 postdocs. She was actually supposed to come to the United States to do another fellowship, but can't now, to talk about all of this, because I feel a great sense of responsibility to give you accurate information and to make it accessible. And so I wanted to make sure that I was understanding things correctly, because I'm not an immunologist. I'm an evolutionary biologist. And I also kind of wanted to touch base with her about, like, if you could give me like 2 take-home messages, what would they be? And so she talked through that with me, and she said, feel free to give them my Twitter, and so that's on that page. Also, her professional website is there. She's really cool. She's a big gamer, and she's cool. So if you are on Twitter, please follow her. But I wanted to tell you that I also reached out to my resources to kind of talk through some confusion and some uncertainty. Okay, so next. So one of the things that she said, and the links to this paper are in your notes. One of the things that she said she would really, really want to emphasize is the extraordinary complexity of the immune system. And so that's exactly what this image is meant to convey, is holy cow, complex. You can't really see that. Holy cow, this is complex. Okay, and if you look over here in the figure legend, I just gave the very top of it on your screen, the rest of it's in your notes. So this is just the interaction network of a small part. Where does it say that? This illustrates the complexity that is only a small subset of pathways that comprise the innate immune system. So the immune system can kind of be divided into the innate immune system and the acquired or adaptive immune system. And so this is just one small part of the innate immune system. Then if we look here, getting into the adaptive immune system, so these are signaling pathways for B cell receptors and T cell receptors. And this is just one of their signaling pathways, and this is just two of the cells that are involved in adaptive immunity. And so what I'm getting at here is that we're going to try to kind of narrow and simplify and make things make sense as much as possible. But please keep in mind that the immune system is extraordinarily complex. It's an incredibly complex system. And so it's a little bit like an orchestra. And so in an orchestra, we know that you have multiple different sections who have to play at specific times. And if one of those sections is off, the whole sound is off. And this is also true about the immune system. Okay, so like the orchestra, where the flutes came in at one part and the percussion came in at another part. You had cymbals at some part. It was loud at some parts. It was quiet at some parts. And all of that's necessary, and all of that has to work together in order for the music to sound awesome. So your immune system is like that. There are so many moving parts, and timing is everything. So you have to have certain components of the immune system active and at high levels at some points and at lower levels at other points. So while we're hearing these reports, particularly about COVID, about immunoglobulin levels, so antibody levels, antigens, we're detecting these cells or those cells, keep in mind that things don't, all the parts of the immune system don't play at max volume all the time. So keep that in mind. And we're going to go through some imagery that I think will help make that make sense. All right, so our immune system. What we have here is just a basic plot. And so on the y-axis is antibody response. So, hang on. Or antibody levels, I should say. So how much antibody is in the system. And then on the x-axis is days after exposure. So how many days has it been since the body became infected with whatever pathogen it is that we're discussing. So here I've just drawn a very technical image to represent the pathogen. So this little pink thing, this could be a bacterium, this could be a virus. I'm using a general image because we're just going to be talking about some very general concepts here in immunology. Okay, so where our little pink thing is here, this would be day 0 of infection. So this is the first entry of this pathogen into the body. And then this little sort of pink plot, this pink line here, is representing the body's antibody amounts along days of exposure. So there are so many things happening in the immune system. For the purposes of our discussion today in this image, we're focusing on antibody production. So this little pink line is representing amount of antibody over days of exposure. And this first little image here, this little blue thing with the little black sticky outies attached to the pathogen, this is our body's first, or I shouldn't say our body's first encounter because that is not true. So this is a B cell's first encounter with our pathogen. And if this is the B cell's first encounter with the pathogen, this is the first time our body's been exposed to this pathogen, this is the first time it's been infected, then this B cell is called a naive B cell. And I have to look at my notes because I misspell naive all the time. So this B cell is naive. And I'm going to write that that's a B cell. Naive, you know, if we say someone is naive, we mean that they haven't been exposed to a lot. Same thing with this B cell. Hasn't been exposed to this pathogen before. It hasn't become specialized. Okay? So the naive B cell encounters the pathogen around day 1, between day 1 and day 3. Takes a while for that to happen. And then what happens next is that naive B cell becomes activated. So these are activated B cells. And that process, we'll talk about that. There's a lot involved. We have activated B cells now. So a little after day 3, and this is a generalized timeline to give you an idea. So we have activated B cells now. All right, cool. So those activated B cells produce 2 types of cells. So they produce plasma B cells, which are these guys that don't have the things sticking off of them. And then the one down here, this one, that has the little thingy sticking off of it, that's a memory B cell. And we're going to come back to the memory B cell in a bit and talk about the memory B cell. But for right now, we're going to ignore our memory B cell. We're just interested in our plasma B cells, maybe. It's not responding. Oh, I'm still erasing. Sorry about that, guys. There we go. Okay, so we're just going to ignore our memory B cell for now. It's very important, and we'll come back and talk about it in a minute. So right now we're interested in our plasma B cells, because our plasma B cells, you might notice, they don't have those little sticky offy things. So those little things that maybe look like fingers or prickles or whatever it is that they look like to you, those are immunoglobulins. Another word for immunoglobulins, the way you probably know them, is antibodies. Okay, so antibodies are important. We need antibodies. Plasma B cells don't have those antibodies. What's that all about? That's because the plasma B cells release the antibodies out. They release the antibodies out into the body to go do their job. So these plasma B cells that were produced by these activated B cells, they produce a certain type of antibody first. So the first type of antibody that they produce, make that thicker. Nope. Okay, the first type of antibody that they produce is called IgG. G, that's for immunoglobulin, and then M. They also are able to produce IgD. Just FYI. We're not going to focus on IgD, we're going to focus on IgM, but I just wanted to let you know that that also is there. Okay, so we're producing IgM. And so IgM is not a highly specific antibody. So these plasma cells get feedback from the body, and based on that feedback, they do something called class switching. So they class switch their antibody or their immunoglobulin, and they can class switch their antibody or their immunoglobulin to a couple of different options. So we have, remember I said this is not working. Come on. We're starting with IgM and also IgD, but we're going to focus on IgM. And so then what the body has to do when it's exposed to a pathogen is then class switch to the immunoglobulin that is specific for that type of pathogen. And we really kind of only think about bacteria and viruses in the developed world, but there are other types of pathogens that our body evolved to deal with. So the one that we're going to be talking about is IgG. And IgG is the immunoglobulin that we have circulating in the highest levels in our blood, and it's the one that's effective against bacteria and viruses. Other potential immunoglobulins that IgM could class switch are IgA and IgE. So IgE, interestingly, is been implicated in allergen issues because it's specific to parasitic worms. And IgA, you typically find it in like the mucus of the the upper respiratory tract, so like the nose. IgG is our specialized, you could think of them as like our specialized weapon, our specialized hit force that's particularly adept at hunting down and killing bacteria and viruses. So IgM, the plasma cells have to release IgM. IgM goes and attacks the pathogen. And then those plasma cells have to get feedback from the body. They get feedback from the body, and then they class switch to IgG. And IgG is really the antibody that's most effective at destroying pathogens or tagging pathogens for destruction. So we class switch to IgG. So where are we now? We're well past 7 days. To get peak antibody production, particularly IgG production, we may go out all the way to 14 days. It takes a lot of time. So we might be way out here to get this. We might be way out at 14 days. Okay. Once the body clears the pathogen, then the body hangs on to, stores those memory B cells that I told you about. And those memory B cells have already class switched. They're already IgG ready. So they don't have to go through that process of producing IgM and getting feedback and then switching to the more effective IgG to fight bacteria and viruses, which is pretty cool. Okay, so how long the body maintains those memory cells, how long the adaptive immunity is stored is different for different pathogens. Okay, so all of this, nope, that's not what I meant to do. Gonna get rid of that. So this that we just talked about, this is all our first exposure to a pathogen. first time our body ever sees a pathogen. This is how it reacts. Oh, I'm still, I don't know why it's mad at me. Let's go back. Okay. So, first time our body gets exposed to a pathogen, we go through this whole process. We have to produce our plasma cells, and we have to produce our memory cells, and we have to switch from IgG or IgM to IgG before we can fight off and clear the pathogen. The second time that we're exposed to a pathogen, the story is quite different. And the second time, the third time, the fourth time, for however long those memory cells are active, this will be true. All right, so now remember that we have those memory cells. So down here at the bottom, right here, we have our memory cells that our body produced that already are IgG competent, ready and rearing to go. So on day 0, we get exposed to the pathogen. So that is this little pink thing right here. On day 0, our body gets exposed to the pathogen, we get an infection. So how does this look? Very, very shortly thereafter, between days 1 and 3, our body actively pumps out those activated B cells. So that's what these guys are. These are your activated B cells. Already very, very early, as early as day 1, day 2, maybe day 3. Okay, by day 3, this is a typical curve. We've got plasma B cells cranking out IgG. So we're reaching peak antibody production at day 3. Whereas back here at our first exposure, we didn't reach peak antibody production until day 7, and remember that many of those antibodies were IgM, and then we had to class switch to IgG, to the more effective antibodies. So we're cranking out IgG at day 3. So then we move forward, get better, body clears the infection much faster, and then now the body has created more of those memory cells. And there are some indications that the more times a body is exposed to a pathogen, the more accurate those IgG are. So the better at killing, the better at their job those IgG are. Okay, so this was all B cells is what we're talking about here. This is all B cells. So it's also important to know, and I focused on B cells here, but the T cells go through a sort of similar process with first and subsequent infection. Okay, so we have a much faster response upon our second and subsequent exposures and a more accurate response. So if we're sort of looking at this whole process, something to know and to understand is that over here in this first exposure situation that's happening here, the symptoms that we experience, the fever, the malaise, the generally feeling like crap, the sneezing, the coughing, the vast majority of those symptoms that make us feel yucky are our body fighting the pathogen. So this IgM right here, one of the things IgM is really freaking good at is activating something called complement. And complement is important. It fights the pathogens, but it also stimulates the release of histamine. It also increases inflammation. So it does a lot of things that make us feel like crap. And so on our second and subsequent infections, well, we'll talk about something else first. Okay. So these symptoms that we experience with the vast majority of our illnesses that we experience, they might be not fun, but they're generally not dangerous. And so for the vast majority of the infections that humans get, we just go through this system, right? Our bodies just go through this, build our natural immunity, and so then the next time we're exposed to the pathogen, we're ready for it. But there are some pathogens where this process of the body being exposed to it for the first time can be extraordinarily devastating. And so I'm just going to give you a couple of quick examples of that, talking about symptoms. So one of those is the flu. And so for most people, the flu just kind of sucks, right? So if this is, and I've given you the links to this is cdc.gov. So for most people, you're going to get fever, cough, sore throat, runny nose, muscle, body aches, headaches, and you're going to recover and you're going to be fine. But for some people, there really, really serious complications will develop. And so people can develop pneumonia, which can cause permanent damage to the lungs. People can have complications with inflammation. So the heart can become inflamed. That's right here. The brain can become inflamed. Muscle can become inflamed. And people can experience multi-organ failure as a result of a flu infection. And this is upon their first exposure to the flu. Other things that can happen is sepsis. Sepsis can definitely be deadly. And then people who have chronic conditions, those are often exacerbated by a flu infection. Additionally, flu is deadly to some people. So we can't ignore the fact that these things that we take for granted or that we think are common, they kill a lot of people. Okay? So flu can have some really severe complications and long-term effects and kills people. One that I think most of us are just really not familiar with at all, because up until very recently it was almost completely eradicated in the United States, and that's measles. So some things that can happen, severe complications, and this blows my mind, and this is why I'm showing you this step by step. So 1 in 5 people who are unvaccinated are hospitalized. So one out of every 5 people who gets measles who didn't get vaccinated ends up in the hospital. That's a lot of people. 1 out of every 1,000 develops something called encephalitis. This is brain swelling. This can lead to intellectual disability and deafness. 1 to 3 of every 1,000 children who become infected with measles die. They die from respiratory and neurologic complications. And measles can cause premature birth and low birth weight. Then we have some long-term complications. You can have this panencephalitis, swelling of the central nervous system. And that can be a very long-term complication of measles. All right, so I've given you the links to this. So for those, that's just 2 examples. But for illnesses like that can have really severe long-term effects or severe complications and result in death, what we can do is, instead of allowing our bodies to be exposed to the pathogen, we can vaccinate instead. And what vaccination does is what I've shown you here. If you look, I've kind of changed what the pathogen looks like. And so it's just kind of like these little lines or little dots. And there are lots of different types of vaccines, and we're going to talk about that in more detail. But what the vaccine does is it exposes the body to the part of the pathogen that it's going to recognize without giving the body an active pathogen. So the body is going to react. It's going to do this whole thing. It's gonna make the memory cells. It's gonna switch from IgM to IgG, and it's gonna start producing those specialized IgG antibodies, because it thinks we're tricking the body into thinking that it's been exposed to the pathogen. And then that way, when we actually are exposed to the pathogen, right here, so we didn't have to be exposed to the pathogen initially, and then that way when we actually are exposed to the pathogen, our body's ready. So we've already gotten that level up. We already have all the specialized weaponry. We got dropped in the game with all of the stuff. We didn't have to go through and get killed 14 times to collect all the specialized stuff. And so that's with vaccination. And with vaccination, those symptoms that people experience, remember that is the body's response. Very many of our symptoms are the body's response to a pathogen. Because the body is able to attack and clear the parts of the pathogen that are injected into our body very quickly, typically you don't have any symptoms, or sometimes you do. Sometimes you have symptoms, but they're much, much less than it had. Guys, I cannot talk today. Had you actually been exposed to the pathogen? Had you actually gotten an infection? So a lot of times people will get the flu vaccine or get vaccinated for something, and then they'll say, the vaccine gave me the flu because they felt like crap. Well, the reason they felt like crap is because it's working. The body is actually reacting to the vaccine, and so complement's getting activated, all those inflammatory responses are happening, and that kind of makes you feel awful. But it's not as bad as actually getting the infection, because one, your symptoms aren't as bad, and two, the actual infection itself that causes those severe complications for flu and for measles and for the other things doesn't progress. There's no replicating pathogen in your body, so you don't have those severe complications or those long-term effects. Okay, so then that leads me to the concept of herd immunity. And this quote, this is Samantha, the same person who I showed you on the previous slide that I went and asked questions. And so this is her pinned tweet about herd immunity. And so she's saying, this is how we protect vulnerable people. Herd immunity isn't what happens when everyone who's vulnerable is dead, or everyone who is vulnerable has severe long-term effects to some infection, or has I don't remember what I was going to say, become infected. So what the heck even is herd immunity? Because this is something that I thought I understood, and I had to go back and talk to her about it, because this is one of my points of confusion, because this term is being misused in the media. Okay, herd immunity. So let's imagine that each one of these dots represents a person. And so this is a community of people, and you're going to do an activity with this with dominoes in your lab towards the end of the semester. But so this is this person's community, and I've simplified it. This person, of course, has contacts in all directions. But let's imagine that this person becomes infected. Okay, they become infected. They have direct contact with these three individuals. They become infected with a virus, so these three individuals now become infected. So this individual has contact with this individual and this one. This one has contact with this individual, and this one has contact with this individual. So what's going to happen? They're going to get infected. Okay, and you get the point, right? So this infection keeps getting spread to this entire community of people. And if all these people have a healthy immune system, and if they don't die, then yeah, they'll develop immunity. So if they have a healthy immune system, which not everyone does, my son doesn't. My son doesn't produce antibodies. And if they don't die, yep, awesome. Now we have immunity. And this system works fine for a lot of pathogens. The common cold, for example. We get the common cold, we feel kind of, we get over it. No big deal. We can allow this system to work this way, which is great, right? But for those things that kill people, for those things that that cause long-term complications or severe complications, that allowing the infection to spread like that, it's unethical and it's awful. Okay, so now let's imagine our system again. And again, I am simplifying this a lot, obviously. All right, so let's imagine instead that this person got vaccinated and this person got vaccinated. Okay? And now this person gets infected. This person was vaccinated, so they already have immunity, so they're not going to develop the infection. So we don't get an infection there. We get an infection here. That infection's going to spread there and there. And then there. And maybe there and there. This infection's going to spread here. Okay, and this is imagery, right? So these two people who I colored in green as vaccinated, they protected all of these people from getting infected. Okay? So what herd immunity is, it's about vaccination. Okay? It's about protecting people from the consequences of infection. And so what herd immunity is how many people in the population do we need to be these people so that the whole population is protected from this infection. Because the reality is, and some of you are probably thinking about this, the reality is that some people can't get vaccinated. Okay? So maybe this person has vaccine reactions. They can't get vaccinated, or they can't get vaccinated to everything. So this person who got vaccinated in green protects that person who couldn't get vaccinated. Maybe this person has cancer and their immune system is massively repressed. They're protecting them. So the goal with herd immunity is to create a situation where enough of the population is vaccinated so that, say, vaccinated, 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 vaccinated. Okay, so that those people who can't get vaccinated because of vaccine reactions or because of cancer or because, like my 7-year-old son, an immune deficiency, he does get vaccinated, but his body doesn't respond like it should. His immune system doesn't function correctly and he doesn't produce antibodies. So herd immunity is getting enough immunity in the population to protect the population from the catastrophic effects of an infection. Okay. So part of the reason, the biggest part of the reason that I wanted to do this at the beginning of the semester is because there's so much misinformation out there. There's so much confusion and it's just overwhelming. Another reason that I wanted to do this early in the semester is because the health authorities are calling for people to get their influenza vaccine. So that's your flu vaccine. And I've put a link here to information from the World Health Organization about influenza vaccination. And every year, of course, the health authorities say, please get vaccinated against the flu, because we don't want you to die from the flu. We don't want you to have horrible complications. But this year, even more than ever, you've probably heard a lot about bed capacity, ICU bed capacity. And so if we have the same levels of flu infection and the same levels of hospitalization due to flu, that's going to take up a lot of our bed capacity. And this year, we also have another massive infection happening in coronavirus that's going to take up a lot of bed capacity. So if we can get everyone who can safely do it to get vaccinated against the flu, then we're going to bring down that number of hospitalizations from the flu a lot, and we're going to be able to save a lot more lives of people who have been exposed to coronavirus, because we don't have a vaccine for that yet. So this is my plug for, if it is safe for you, to please get vaccinated against the flu. And that's our preview to the immune system, and we're going to come back, circle back to this, and get into a lot of detail in our whole week that we spend on the immune system. Thanks for hanging out with me, and I hope to hear from you. If you have any questions, please feel free to ask. And I'll see you again on Wednesday.